continuing our overview of inverse functions. The figure on the left is the one we used in the last video to show that f of x and g of x were indeed inverse functions, that when you swapped ordered pairs, you indeed ended up with a graph that passes the vertical line test. So that means that the original graph must have passed the vertical line test to be a function and the horizontal line test to be a one-to-one. Now the figure in the right illustrates a similar situation where you see the symmetry about y equals x, and you notice a shift in the notation here. Now when you definitely have an inverse function, the notation is red. It looks like a -1 exponent, but that's not what it means. It's red. Y equals f inverse of x. And what it means is that if you have the graph f of x sending the sending the value a to the value b, then this guy is going to send b back to a in every single scenario. Okay? So now rather than calling them f and g, we use this special symbol, and again it looks like an exponent but it's not, to mean swap x and y. So basically, to find f inverse, if we want to process here, to find the formula for f inverse of x, we're going to let y equal f of x. We're going to swap x and y in that formula, and we're going to solve again for y. To give us the inverse formula. Okay? Now when you do this, I would like for you to notice that intrinsically the domain of 1 domain of the inverse function, for example, would have to be the range of the original function, because you're swapping all the ordered pairs. And likewise, the range of your inverse function will have to be consistent with the domain of your original function. Okay, now let's take somebody that we can graph, for example, with our graphing techniques. So let's graph f of x equals x cubed plus 1. So our graph of x cubed plus 1, it looks like the curve we're familiar with is y equals x cubed shifted up 1. I've drawn in the line of symmetry, which is y equals x. But I want to look for a moment at the algebra process. What I'm going to do, again, step 1, is I'm going to let y equal f of x. Step 2, I'm going to swap x and y. And I'm bothering to do this to find an inverse because I know that the red graph, my original, is indeed one-to-one. Okay, so swap x and y, which leaves us with x equals y cubed plus 1. And then step 3 is we're going to solve for y after we've swapped, and when we do, we'll have f inverse of x. Okay, so let's go ahead and solve for the inverse. So now that we have swapped x and y, we'll solve for y. And in doing so, we'll need to subtract 1 from each side, and then take the cube root of each side. So we'll have the cube root of x minus 1 equals y. So that's our f inverse of x. Okay, and now let's graph the inverse on the same coordinate axes. Okay, I've drawn it in for you, a rough sketch. You can see that the point 0, 1 does indeed become the point 1, 0. When you swap x and y, -1, -1 stays the same. The point 1, 2 becomes the point 2, 1. And they're symmetric to each other about y equals x. And notice that, again, if a function does have an inverse function, the original function must be 1 to 1, which means you pass the vertical line test to be a function and the horizontal line test to be 1 to 1. It also means that your inverse is a 1 to 1 function. It's a pretty nice process. Okay, so again, swap x and y, solve again for y. You'll have a formula for the inverse in terms of x, and then you can see the symmetry between the graphs of the two functions.